Hey, how we doing everyone? Welcome to the Bearded Medic. This video will run through the innate response to an extracellular pathogen, leading up to the cardinal signs of inflammation. But before we start, if you haven't done so already, watch the introduction to the immune system video so you have solid foundations to build upon. So as we discussed in the previous video, in order for pathogens to enter the body, they must first overcome the body's primary defenses, be it physical, chemical, or a biological defense. Think of a simple cut to the skin, which allows pathogens to bypass the tight junctions and enter the body. Any damage to these defenses, whether by a pathogen or not, can release damage-associated molecular patterns, or DAMPs for short. These are cell components like RNA, DNA, and other molecular proteins that leak out of the cell because of the damage. Pathogens are foreign material to our own bodies, hence they have pathogen-associated molecular patterns, or PAMPs for short. Both DAMPs and PAMPs are identified by pattern recognition receptors, or PRRs, on cells. The function of pattern recognition receptors is to identify if encountered material is self or foreign and respond accordingly. Now there are many families of pattern recognition receptors, each with their own subtypes that identify different parts of pathogens or even our own material. Some of these receptors lie extracellularly and some of these are intracellular. Each can lead to varying responses. For this instance, we will talk through the process following extracellular recognition of bacteria by phagocytic receptors and the toll-like receptor family. Firstly, we'll go through the phagocytic receptors. So we have our pathogen, which is a PAMP. Tissue-resident phagocytes like dendritic cells and macrophages recognize the foreign nature of the pathogen via phagocytic receptors. This can be due to complement proteins like C3b opsonizing, which is to say, marking the cell for destruction, or even direct recognition of the foreign material. We'll run through the complement system in another video, but for now, think of C3 as a protein that splits into an A and B subunit when it encounters a foreign pathogen. We'll get to the role of C3A later, but C3b sticks to pathogens and marks it for destruction by phagocytosis. Phagocytic receptors therefore induce phagocytosis. The pathogen is internalized and enclosed in a phagosome. Cells also have lysosomes, which contain lysozyme, nitric oxide, and other antimicrobial peptides. This fuses with the phagosome to form a phagolysosome. The resultant environment is highly acidic due to the proton pumps from the lysosome pumping H+ ions into the phagolysosome, degrading and destroying the pathogen. The product is then expelled from the cell and cleared from the system. So for phagocytes, they recognize the pathogen with phagocytic receptors, enclose it in a phagosome, merge the phagosome with a lysosome to make a phagolysosome, and let the acidic and enzyme-rich environment obliterate the pathogen. That's phagocytosis in a nutshell, destroy as much foreign pathogen as possible. However, we still need the help of more immune cells to ensure this. That's where we'll talk about toll-like receptors, and we're still with our tissue-resident cells. As with phagocytic receptors, toll-like receptors identify the pathogen as foreign. This leads to a signaling cascade that causes changes in the transcription rate of certain proteins. For now, the main proteins to be concerned with are cytokines and chemokines. Transcription rates are changed from the activation of what's called transcription factors. The transcription factor NF-kappa B increases production of the major pro-inflammatory cytokines. These are interleukin 6, interleukin 1 beta, and tumor necrosis factor alpha. These are extremely important to remember. Here's why. These three are the main cytokines that allow more infiltration of immune cells into the tissue to eliminate the pathogen. They do this by causing inflammation, hence they are pro-inflammatory. They activate the vascular endothelium, causing the tight junctions between endothelial cells to loosen. The vessel is therefore more permeable and fluid leaks out. This buildup of fluid is called swelling or edema. Activating the vascular endothelium also causes nitrous oxide release, which leads to an increase in blood vessel diameter. This increases the blood flow to the area, also slowing that blood down to allow more immune cells to leak out. This change in blood flow increases the temperature and gives a red appearance to the area. Finally, activating the endothelium causes peptides called bradykinins to be released. They sensitize pain receptors, or nociceptors, to pain. This means when anything pushes on those nociceptors, such as the swelling, there are increased pain signals. These cytokines therefore lead to the cardinal signs of inflammation: edema, heat, redness, and pain. or in their Latin names tumor, calor, rubor, and dolor. Be aware that there is a fifth one that was added later, which is loss of function to the area. On top of these effects, the pro-inflammatory cytokines have further actions. IL-6 increases chemokine production and causes systemic effects such as raising body temperature and increasing acute phase protein synthesis, like C-reactive protein. IL-1 beta upregulates adhesion molecules for recruitment of more immune cells, which we'll get to later. TNF alpha causes further cell destruction by activating pathways that induce cell death. So essentially remember, recognition of a foreign pathogen by cell membrane toll-like receptors leads to an increase in the NF-kappa B transcription factor. This leads to an increased production of the pro-inflammatory cytokines IL-6, IL-1 beta, and TNF alpha, which exert vascular effects leading to edema, heat, redness, and pain, the cardinal signs of inflammation. Now, of course, we need more immune cells, namely phagocytes, so we can destroy as much pathogen as possible. These cells don't just flow out of the blood vessel, they need help to get out. So how do these cells enter the tissue? Remember NF-kappa B? It also codes for the chemokine CXCL8 and adhesion molecules like E-selectin. Chemokines are proteins that induce movement of cells, or chemotaxis. CXCL8 and E-selectin, along with the pro-inflammatory cytokines and complement proteins like C3a and C5a, are important for immune cell recruitment, mainly neutrophils, which are the highly destructive phagocytes. For some context, if we go back to C3 from earlier, how it's broken down into C3a and C3b, well, C3b also goes on to cause the C5 complement protein to break down into C5a and C5b. Our C5a and C3a can go to the blood vessels to recruit neutrophils along with CXCL8. Neutrophils normally just flow around the blood and have surface proteoglycans that form weak attachments to the adhesion molecule E-selectin on the endothelium. However, upon infection, IL-1 beta and TNF alpha have increased the expression of adhesion molecules on the vessel lumen. This means neutrophils can continuously bind and break bonds with more E-selectins, causing them to roll across the wall of the endothelium in a process called margination. At an endothelial junction, neutrophils are then firmly attached to the ICAM1 on the vessel via the neutrophil surface receptor LFA1, which is an integrin. The CXCL8 mentioned earlier binds to the CXCL8 receptor on neutrophils, causing the neutrophils to squeeze between the endothelial junctions and out the lumen, a process called diapedesis. The neutrophil then follows a trail of C5a and C3a like breadcrumbs to the site of infection to exert their actions. So think selectin, to choose cells, adhesion, to make cells stick to the endothelium via integrins, and chemokines, to escort the cells to the site of infection, as the multi-step process. So finally, we'll have a look at neutrophil action. Neutrophils phagocytose pathogens, except they also use their granules, for which they have three types: primary, secondary, and tertiary. Each have their own set of antimicrobial peptides to digest pathogens. This is the important thing. Binding of the secondary granule forms NADPH oxidase. This causes the formation of free oxygen radicals that lower the pH of the phagosome. This activates the enzymes and peptides in the granules in order to destroy the pathogen. That's one mechanism. Another is called the respiratory burst. This is when they propel toxic oxygen species to trap extracellular pathogens and kill them. However, this renders the neutrophil unable to regenerate, hence it undergoes apoptosis, which is cell death. Neutrophils unravel their DNA, causing them to swell and burst. Their granule contents destroy anything surrounding, aiming to destroy as much bacteria as possible. This is called a NET, neutrophil extracellular trap. So overall, neutrophils phagocytose using granules to hydrolyze the bacteria. They propel toxic oxygen species in a process called the respiratory burst, but this leaves them severely damaged, leading them to go out with a big burst of their granule contents to destroy any surroundings, the neutrophil extracellular traps. So that concludes this video. We spoke through the process of extracellular recognition of bacteria by phagocytic and toll-like receptors once they breach the primary defenses of the body. We went through the process of phagocytosis upon recognition by phagocytic receptors, and we also went through how recognition via toll-like receptors leads to the major pro-inflammatory cytokines IL-6, IL-1 beta, and TNF-alpha, also showing how their actions on blood vessels cause swelling, redness, heat, and pain, the cardinal signs of inflammation. We also went through how neutrophils are recruited into the tissue, and the action of those neutrophils to destroy bacteria, like phagocytosis, respiratory bursts, and neutrophil extracellular traps. Bear in mind this process differs for intracellular recognition of pathogens, which will be discussed in another video. So that was a lot. Hopefully visualizing this made it simpler and manageable. If you have any questions, be sure to leave them in the comments, and make sure you try the quizzes on Instagram to test your attention. If you were happy with the video, leave a like and subscribe for more. Thank you for watching, and see you in the next video.